Okay, today we're just going to be reviewing for the exam. You may be wondering about homework. I intended to give you a homework assignment that would be due tonight because it's stuff that would be covered on the test. But somehow in my brain, I was thinking, we'll just not have the assignment due until Wednesday so they can study on the test, forgetting that it was going to be useful for the test. And so then yesterday, I was like, wait, I can't give them one now because it's too late, or I can't give you one on Sunday, just do on Monday. You got to have, it's only fair to give you a little more time on it. And so I didn't post it yet. So I will post one after lecture today that won't be due until Wednesday, but is useful material with regards to the exam. Right, so you don't have to do it before the exam because it just wouldn't be fair. But at the same time, it is useful if you at least look over it for some practice. Is that all clear? I don't want anyone saying, I didn't understand what he said. Second thing, remember that the reading quiz, I was going to postpone until Wednesday, but I couldn't, so it said it was due on Friday. And it's still going to be due on Wednesday. Everything will say it was due this past Friday. So make sure that by Wednesday, you do the reading quiz that said it was due on Friday and the reading quiz that says it's due on Wednesday. So, again, don't want anyone to forget. And while I'm on the reading quizzes, remember that if you missed a reading quiz in the section that's going to be covered on this exam, you can still get 50% doing it before the exam. That's why you don't have the reading quiz grades come in until the exam time, because I want to encourage, if you missed one, to go through and do that in preparation for the exam. Okay. Yes, Emily.
Lab quiz 7, I think, is not in the lab section. It's like not for credit.
Oh, okay. Probably not. I will have to look at it. I'll have to look at it. All right. A reminder for the last 3 problems. If you are wanting me to hand grade, which I recommend doing this even if you think you have them all right, just in case you made a little mistake. Write it out in a formal way where you have a clear figure that shows what you need. So if, for instance, you have a ball rolling down a plank and it asks about the speed at the bottom of the plank, you should have a picture that shows the plank with the ball at the top and the ball at the bottom. And the logical way to solve that problem, that's of course part of physics, is that you would be using the work-energy relationship. And if you're going to use the work-energy relationship, you would put the kinetic energy on the top and the kinetic energy on your figure as well. Why do I want you to do that? Because it's going to make sure you do it right? It's helping you toward the solution. Make sure you include the concepts you're going to use. So once again, for the example I just gave, you would say, I'm going to use the work-energy relation to calculate the final speed at the bottom based on, as long as you, for that one, it's reasonably simple. You just have to say, use the work-energy relation and you'd be there. But you need to put that out there so I know, oh yeah, that person knows where they're going with this. Then you have the equations. I didn't put the equation, well, I guess I did. Working from standard equations, make sure you write down the equations you're going to use. And they need to be equations that are on the equation sheets, ones that are generally true, not special case equations. And then show your work. And that will allow you to get back a lot of credit, even if you made a mistake, as long as you knew where you were going, how to do it. And of course, I recommend you do this for every problem. But the last 3 are the ones where it can make a difference on the grading, not just on your answering correctly. So now I say on every problem, the knowledge questions, this isn't going to help you with. But the application and the synthesis, both, this should be helpful. And as I said, only the synthesis will affect your grading if I go through grade by hand. Of the people who missed 2 or more, all but 2 people, their grade went up with the partial grading. And I would like everyone's to go up with the partial grading in that case, not just all but 2. Okay. By the way, notice my words here, not to be harsh or anything, but if you take special case equation and just put the numbers in, you've done a math problem, not a physics problem. What makes it a physics problem is that in physics, we're trying to figure out what ideas are at play and how they fit together so that we can explain how something works. We're not just saying, here's the equation, here I put the numbers in, there's the answer. Right? That's math. In physics, it's about the thinking part. That's why just using a special case equation doesn't get you the credit. Not because, oh, you just got the right answer the wrong way. It's because I want to see that you've gone through the physics thought process. All right. Our test is over chapters 9, 10, 11, 12. By the way, these are already available on the OneNote. I'm doing the lecture today using OneNote. So if you go to OneNote, you have all the slides that are already available to you. So chapter 9 was equilibrium. Equilibrium, it means equal forces. But it actually, in practice, is more than just equal forces. It has two conditions. Some of the forces is zero, and some of the torques is zero. Now keep in mind, some of the forces is zero, according to Newton's second law, directly implies acceleration is zero. It does not imply speed is zero. Almost every equilibrium problem we do have speed is zero. But that is not the definition of equilibrium. You can have an equilibrium problem where something is moving. It just has to be moving at a constant velocity. Likewise, the rotational equivalent for Newton's second law, the sum of the torques is equal to moment of inertia times angular acceleration. The equilibrium condition that the sum of the torques is zero implies angular acceleration is zero, not that it's not rotating. So make sure you know the conditions. And remember, the sum of the torques one is the one that we often go to first. Because when you sum the torques, you get to choose where you want to sum them. If it's in equilibrium, you can sum the torques about any location. And you will find that the sum of the torques is zero. And so by choosing an appropriate location, you can make one or more torques have zero, or one or more forces have zero torque. Because remember, torque is R cross F. And of course, we're doing a review. I'll write this down. You will definitely have to do something that involves the right-hand rule. And I'm sure you'll have to have a question that shows that you know what the cross product means. So let's start with what this means. R cross F, any equation that has a cross product. Right now, this is the only one we have, I think. But we will have more before the year is through. What does it mean if a math problem has a cross product? If it didn't have vector signs, what would the cross mean? You learned this in grade school. Multiplication. Right? Without vector signs, that would just be R times F. So with vector signs, the times becomes cross. And what does the cross mean that's different from times? We're multiplying just the perpendicular parts. So if I have a force that's acting parallel to R, then there's no perpendicular parts, and this is going to be zero. So we have to define what R is before we can go forward. R was the vector that points from the location I'm summing torques to where the force acts. So remember my example, the very beginning of this. Now I've got these heavy masses. If I hold this out here, the natural place that I would sum the torques is about the joint. Why is that natural? Because I don't know what forces are going on at the joint. But if I sum the torques here, the perpendicular distance for those forces is zero. And then I just have this radius times that force, which conveniently enough, they're perpendicular. And of course, I do have another force, a muscle here, that's coming out and attaching somewhere here that's making a counter torque. And what do I know about that? A little more than I wish because of the surgery to fix that problem. But you can have problems like that. So sum of the torque, R cross F, you have to know R is the distance from where you're summing the torque to where the force acts. F is the force, and the magnitude. This is, oh boy, that's not a vector sign. It's kind of overkill. If I put the absolute value signs for a vector, that means the size of the vector, how big the number is without the direction. Is radius perpendicular to the force, what we sometimes call the lever arm, which is equal to RF times sine of the angle between the two. And I drew a picture before just to demonstrate. If here is F and here is R and theta is the angle between the two, then the opposite part is the perpendicular part. And that would be hypotenuse times sine of the angle. So that's why it's RF sine theta for the magnitude of the torque. So you're going to need to be able to do these calculations with torque. And I'm going to do a problem in just a minute. Remember, there were 3 types of equilibrium: stable, unstable, and neutral. Stable equilibrium, you displace it, it will come back. Unstable, you displace it, and it's going to cruise away. Simple example of unstable is if I have a ball on top of a mountain. It's balanced in the center. If I move it over to the side, it rolls down the mountain. That was unstable. If I have a ball in a valley, it's stable. If I displace it, it'll just roll back to the bottom again. And neutral would be a ball on a flat surface. If I displace it, it'll just be happy in this new location and not come back and not go off. So let's do a quick problem. This is a problem I put on a test in previous years. NFL rules specify the football goalposts are 18.5 feet apart. So that's the distance from here to here. I'm going to zoom in. 18.5 feet across. And the crossbar is 10 feet off the ground. Just to be consistent. 10 feet off the ground. And the single standard is buried 53 inches. So this thing is going down 53 inches. That's a 5 followed by 3. Below the ground. And it's placed with an offset of 2 feet like that. I think I've got all my numbers in there except for the mass of the fan. So now we're going to have a fan that's standing here. Yeah, you may ask, why do I ask a question like this? I remember my first year at Wazoo. I was at a football game. We won. The fans rush out there in the field, climb on the goalposts. You have a whole bunch of people on the goalposts. The goalposts fall over. The fans then carried the goalposts out of the stadium, down Stadium Way, and left it outside of the Coug, which was a local bar. Kind of, yeah. Yeah.
Did you partake?
I did not. I did not partake, nor did I participate. 2 different questions, both of them the answer is no. What was disgusting is the guy who was standing next to me was chewing tobacco. And after a big play, woo, and guess what comes all over me? The stuff that was in his cup. Yeah. Yeah, it was really fun. Just a little note. Bad things like that do happen. I've seen plenty of people, like during the national anthem, the guy next to me ralphed on the person in front of him once. This is at an NFL game. But yeah, bad things happen at games. You just have to wear your raincoat. Be prepared. So let's do this problem rather than talk about things that aren't going to affect your test grade. So my question is, how much horizontal force does the ground need to apply additional to what it already needs to apply to hold it up for that 95 kilogram fan? So the first thing I have to think about here is, well, I've got most of my picture, but I'm going to redraw it specifically. But what's the concept? How am I going to figure out how much additional force the ground needs to apply to hold that fan up? What physics idea am I going to use?
So you could treat it like a lever.
Okay, could treat it like a lever. That's an accurate statement. It's not the words I'm going to use, but it's an accurate statement. If you put that down, I would at least give him 2 out of 3. on the concept just right there. What I'm going to do is I'm going to use it's in equilibrium. If it doesn't start to fall over, so sum of the torques is equal to 0. Sum of the forces is also 0, but I'm not even going to focus on that. I'm going to use sum of the torques as 0. Choose ground level on what I call a standard. That's my entire concept right there. It's an equilibrium, so the sum of the torques is 0. I don't have to put the sum of the forces 0 because that's not the part I'm using. And then I'm summing the torques about the ground level on the standard. The reason being is I know there's going to be forces. It says treat the standard as if there's a force acting at ground level and at the bottom. I don't know what the force is at ground level. It doesn't ask me for it. So I'm choosing to set that as where I'm going to sum the torques. Now I need to draw a picture. And I'm going to draw 2 pictures. First, a top view. So in the top view, I have something like this. Because I'm looking straight down the goalpost, so I put 2 bigger circles for each post. And then I have the standard coming down here 2 feet away. And I have my person is right there. Why did I draw this view? Certainly not because it gives me everything I need, but because it allows me to see my geometry for my lever arm. This distance here, that's a T instead of a perpendicular, is the perpendicular distance that I'm going to use. And we were given that this distance here is 2 feet, and the distance from here to here is 1/2 of, 18.5 feet? Yep. So that's 9.25 feet there. So I can calculate my R perpendicular here using the Pythagorean theorem. So that's the top view. Now side view, and the side view is going to be a little odd because I'm just going to draw it like this, looking at the appropriate angle where this distance here is the R perpendicular I just calculated. So I'm looking at it, here's the goalpost, looking at it so it's tilted or twisted, so I have that perpendicular distance is what I'm seeing. So that side view is viewing from this viewpoint. This is supposed to be an eyeball, by the way. That's how we physicists do it. Let's wait till we get to optics. So that's what my side view is seeing. And then I have, here's the ground level. So the distance below the ground to the bottom was 53 inches. The distance from here to here is 10 feet. And now I'm going to put the additional forces necessary. Now this last part is probably the most confusing of all, because we know we have the weight of the goalposts and we have the forces that were necessary to hold the goalposts up, and those are all already balanced. I'm only calculating the additional, so I'm going to say, let's forget all of those because we know the sum of the torques for those are already 0. And only going to look at the additional. So the additional here is force of gravity for the person, mass of the person G. If that's pulling, is that going to make this rotate clockwise or counterclockwise? Would that force make my standard as drawn go clockwise or counterclockwise? Clockwise. Is that a positive or negative torque? That's a negative torque. So I'm going to need a positive torque about this location for the bottom. So what direction will the force have to be on the bottom to counter that torque of the person? To make a positive torque or a counterclockwise torque, what direction is it going to have to point? I got to look your way. That's correct. See, if I look at it my way, it's incorrect. Turn around. So here I'm going to have the force additional. So I'll call it force A. There's also a force here. I'm going to call it force unknown. Force U for force unknown. It's unknown because I not asked for it, and I'm not going to calculate it. The reason remember I started in my description saying where I was going to sum the torques. What if you didn't know at that point? Well, now you do. Now that I've drawn the forces, I'm like, okay, I know the one at the top. I'm looking for the one at the bottom. I don't know the one that's acting on that green dot, so I better sum my torques about there to make it the shortest possible problem. Now that was R perpendicular. Makes my life easy. G for ground. Sum of the torques about the ground is equal to the R perpendicular that we already calculated well, we didn't calculate, we had an equation for it, times the force gravity of the person. And as you already said, that's a negative torque. Using the right-hand rule, my fingers go first in the direction of R, then the direction of the force. My thumb points in, hence negative. So I put a negative sign out here, plus 53 inches times force additional plus 0 times force unknown. You do not have to put in the 0 times force unknown because you know that's 0. Everyone here, face it, you're easily the top 10% of all students at Union College, right? Everybody agree?
Oh, yeah.
Oh, yeah. Thank you. I know that you know anything times 0 is going to be 0. So you don't need to show that here. I'm not going to question you on that. Yes?
Can you go back to the right-hand rule and do that one more time?
I thought you wanted me to go back to repeat once again that you're the top 10%. Okay, the right-hand rule. Let's take the example that we did here. I wrote that R perpendicular. My R vector for the force of the person, there's the R for the person vector, right? And so I take my hand and I orient my hand so my index fingers are pointing in the direction of that. So here my fingers are pointing that direction. And then I keep my fingers pointing that and I orient my hand so I can bend my middle fingers to point the direction of the force. Well, the direction of that force is down, so I need to orient my hand so my fingers are still that direction, but now I can bend my fingers down. And then my thumb points in, which we call negative.
So if the thumb is pointing out, then it'd be positive.
Right. So let's just apply that now to the second one. So for the second one, there was the R perpendicular. So it's going down. So I take my right hand, and how do I orient my hand initially? Like Sarah's. Both Sarah's. So my index fingers are pointing down. And then I orient my hand so I can make my middle finger point the direction of the force. So I orient it like this, and my middle finger can point the direction of the force. Then my thumb is pointing out, hence positive. Now keep in mind when you're doing the test, that paper can rotate a lot more easily than your wrist and arm. So if you have a picture that's making you do this kind of thing to try to get it, just rotate your paper to make it comfortable, okay? There's no need to contort yourself. Wes?
What if when you're drawing your diagram, you just decided to draw it the opposite way?
That would be fine.
And so
That would be your decision, yeah. It'd still be correct. You still come up with the right answer in the end. No, you must do it the way I did it. It's not my way or highway. You know how it is. No. I've seen student complaints, fortunately about other teachers and never about me. You know, if you don't answer the way he wants, you get a 0, even if you're right. You know, you have to think exactly the way he does. Never should that be the case. You're not in college to be indoctrinated. You're in college to learn how to think for yourself. So if you have a right answer, it doesn't matter if it's a different right answer than the teacher's. There's some subjective classes where that becomes more problematic, and thankfully physics is not one. All right, so we have our equation. So now we're ready to solve this bad boy. We're looking for this force. So I'm just going to add our perpendicular force, gravity, person to both sides. And I have 53 inches. Divide both sides by 53 inches. And I have the force additional, I think I said applied instead of additional, is equal to the square root of, I'm going to have to change that from feet to inches. So 2 feet is 24 inches. And 9 1/4 feet is 9 times 12 is 108 plus 3 is 111. Yeah. Or, what was that? Because Pythagorean theorem says that the hypotenuse is equal to the square root of each side squared. And yeah, this is the perpendicular distance that's perpendicular to the force of gravity. I could have gone one step further and then backed out using sine theta. That is, I could have calculated what that is and then use sine theta, and it would have been just more calculation. Yeah. Okay. So, yeah, 9 times 12. I did that right? 9 times 12 is 108 plus 3 inches for a quarter, and so that's 111. Yes, Michael.
So the two diagrams showing you two perpendicular forces.
The first diagram was looking straight down so I could see what that perpendicular distance was from the crossbar to where the person's standing.
Okay.
That was the whole point of it, the end of why I made it.
Okay.
Then the second one was for the torques. Usually, I actually will give you credit if you have two that are really necessary and you have one of them. I'll usually give you credit. I mostly just because I want to be generous, not because that's the best way to do it. Okay, force of gravity was mass of the person times g. Mass of the person we had was 95 kilograms. G 9.80 meters per second squared. Divide that by our 53 inches. And I know I put all the numbers in. I'm a physicist. I don't really care about the numbers. So I'm not even going to put these in the calculator. It does leave me with an empty feeling to not get a number after I've done all of the work. But that's how you do it. I did all of this in gruesome detail, taking up half of our time by now, because I want to make sure you understand what is expected for you to put when you're doing the work. So there are a couple things that I didn't write down that I should have. Or did I? I have some of the torques is equal to 0. You need to have that equation, and you need to have torque equals R cross F, which I'm sure I wrote somewhere. Nope, didn't write it down. You need to make sure you have those equations without any numbers in them, because those are the starting equations. Any questions about the whole process here?
Can you explain one more time about the square root thing at the end?
About this square root right here?
The other one. There's another one. Right. Right there.
That is this.
It is this.
It's the same thing. The only difference is I changed from feet to inches. So the numbers, instead of being 2 or 24, because I had multiplied by 12. Instead of being 9.25, it's 111. So it's the same.
Can you walk me through how you decided to do the perpendicular arm? So if you scroll over to the other side, how you figured out how to do the arm, the perpendicular arm, like what made you think of doing that?
Okay. Here's a problem, not for you, but for me. I've done these problems so often that I see it and I know where I have to go. Right? You're not in that place. Right? If you were in that place, you're like, why have I taken this class? So when I looked at this problem, the first thing in my thought process was, what can I use to solve this? And I came up with equilibrium because, you know what? There's no motion, and that's the only thing we have for no motion in this class. It's equilibrium. And so I knew it was going to have to be an equilibrium problem just because of that. So then the equilibrium conditions give me sum of forces is equal to 0 and sum of torques is equal to 0. Because I had forces in multiple directions, I immediately wanted to go to sum of the torques is 0. It's generally going to be what you have to do if you have forces in more than one direction. So I went to that. Also, looking at the forces, I have forces that I really care about 3. How do I know which ones I care about? Because of that word, in addition. It said what additional force will be necessary. So I can take this problem and say, okay, it's an equilibrium without the person, and so all the forces that were present without the person, if I do my equilibrium condition, they're going to come out to 0. So I'm just going to drop them from my calculation because those are all going to add to 0. And I have 3 additional forces, the additional force of the ground at the bottom, the additional force of the ground at the ground level, and the additional force of the person. So 3 additional forces, of which I only know 1. If you just use the sum of the forces equals 0, one equation can only find one unknown. Now I do have vertical and horizontal directions to worry about, but you know what I didn't? I didn't write one force here. I didn't even think about that force until now. Bad Richard. I didn't think about it because I knew it's not going to be part of my solution, but still I should have remembered there's also going to have to be a additional vertical force pushing up to hold the person up, right? If you didn't have an additional upward force, the whole system would sink into the ground. I didn't even think about that until now. So there's actually 4 additional forces. But if I choose the ground level, I have 2 forces that are actually where the standard goes into the ground. The upward force due to gravity and the sideways force at ground level. So that's the reason to go with the sum of the torques. It makes those terms give 0 torque. And so then at that point, then it's applying. So at that point, it doesn't become easy because applying the sum of the torques equals 0 requires you to go through the right hand rule, not with your left hand, but with your right hand. So it's not simple at that point, but you're done with the thinking part, and now you're into the applying part. Further questions here?
I'm confused on the top view and the side view. Like, how did you get R perpendicular on the side view, translating it from the top view?
Okay, so it's it's harder without having the picture. So I will be the goalpost. So the goalpost, essentially, because I can't go forward and out, I'm moving my hands here. So my hands are like the uprights. And there's a bar going between my elbows. And so the first picture is rotated like this. The first picture is rotated, so you see the distance perpendicular from here to here, which is not the same as from here to here because it's going like this.
Okay.
That's what you were wondering about? I don't make a perfect goalpost here, but moving on. That's chapter 9. Chapter 10, rotational dynamics. This is where things like the problem I mentioned at the beginning, if you have a ball rolling down a plank, comes into play. If the ball slides down the plank, it's actually a simpler problem than if it rolls down the plank. If it slides down the plank, you're going to have the force of friction that can take away some energy, or if there's no friction, it just goes without. And the work-energy relation is pretty straightforward. You just calculate what the net work is, and you calculate the kinetic energy start and stop, the potential energy start and stop. You put them all together into the equation that says work net, well actually work non-conservative is change in kinetic energy plus change of potential energy. But if you have something rotating, you're going to have an additional kinetic energy term, 1/2 I omega squared. And so you have to be a little more intentional there. So make sure you know these terms, angular momentum, and can calculate it. Angular momentum has the symbol L. I is the moment of inertia. Make sure you can calculate a simple moment of inertia. If I say it's a hollow sphere of this mass, you need to think in your head, well, I look in my table for the moment of inertia for a hollow sphere, and I see that it's 2/5 mr squared, boom. Right? It's not like you have to calculate the physics of, the calculus of it, unless you're in physics 251, excuse me. But you need to be able to look that up. And they say if it's rolling, it's going to have kinetic energy due to the rotation of 1/2 I omega squared, plus the kinetic energy of translation 1/2 mv squared. So you have kinetic energy rotation 1/2 I omega squared. I should have put here L is equal to R cross P is a correct form of angular momentum. Using that equation, you can use conservation of angular momentum to analyze a falling ball or a ball flying through the air. Why would you? Only if you're a glutton for punishment. You like to make an easy problem hard, but you can't. So make sure that you can calculate the moment or the moment of inertia, the angular momentum. You know how to get the kinetic energy rotational. You know torque is equal to R cross F. And the net torque equals I alpha is equal to I delta L over delta T. Excuse me. Is equal to delta L over delta T. I think I made that mistake on the equation sheet, actually. I'll check and make sure it's on the equation sheet for tomorrow. The net torque is the change in angular momentum over change in time, just like the net force was change in linear momentum over change in time. This last equation, remember we talked about this. We talked about how that accounts for you can ride a bicycle with no hands. Because you have angular momentum in those tires, if you lean to the left about the ground, that's going to create a torque that is back to your rear. And so the angular momentum of your tire, if you're traveling forward, the tire's going like this, you wrap your hand in the direction of the rotation, your thumb points in the direction of angular momentum. If you're riding forward on a bicycle, your angular momentum is pointing to your left. If you lean left, it creates a torque to the rear, and so the angular momentum is going to shift toward the rear as per that equation. Now, the bigger your angular momentum, the slower the shift is going to be, because for the same torque, the amount that the tire has to rotate to create the backward change is smaller. Right? If you have a really big torque, just a small rotation will make a pretty big backward angular momentum. Whereas if you're going really slow, the tire has to go all the way like this to make the same thing. So that means that when you lean, instead of just falling over, the front tire rotates and you turn. The faster you go, the better it works, until you go really fast. Something I didn't talk about, I did not know this because I am not a motorcyclist, but a student over a decade ago now said, oh yeah, if that's true, why is it when I'm riding down the freeway on my hog, I push forward on the handlebar on the right side to turn right? Anybody here ride a motorcycle, experience this? Yeah, I didn't either. I was like, I'll have to look into that because I don't know. Right? It just seems counterintuitive that you push forward on the right to turn to the right. On my bicycle, I always pulled back on the right to turn to the right. Well, here's what's going on there. When you push forward on the right, it starts to dump you to the right. But as you start coming over to the right, it creates the torque that's going to make the steering wheel turn to the right. So you push forward to make you start to fall to the right, and then the steering wheel will come to the right because you're falling to the right, and then you're pushing forward on it to keep the steering wheel from coming back on you, and that's how you make the turn. It's pretty complicated, isn't it? All because physics. All right, so make sure you can work with these things, be able to apply the rotational equivalent Newton's second law, which we've already talked about, solve rotational dynamics problems using the work energy or forces and torques. Forces and torques is going to be harder almost always than using the work energy relation. So focus on using the work energy relation unless you have to. You know, things like the ball rolling down the ramp. You can solve it with forces and torques. You have to make a relationship between angular acceleration and linear acceleration, and you have to calculate torque caused by friction and so on, but you can do it. It's just a lot harder. I have 8 minutes left. I have 2 problems here. Let me very quickly go through the last 2 chapter reviews and come back and do these problems. Very quickly, just so we can say, yeah, we did look at the ideas that are going to be on the test. So, okay, good. I was like, if this doesn't show up, well, we won't. So chapter 11 was fluids, static fluids. Chapter 12 was fluids that were dynamic, moving. So chapter 11, we had static fluids. First, we just had the identification of a solid versus a liquid versus a gas. And of course, how does a plasma fit in? How does a colloidal suspension fit in? Just talking about the states of matter. And then once we identified the states of matter, we said anything that flows is a fluid. All of this is just definitional. Now you should understand physically why there's a difference between a solid and a liquid. In short, a liquid, you have the molecules moving fast enough that they have more energy than the maximum energy that can hold them in their fixed place, so they break free. You could actually think about this kind of like if you have a block of, I'll say a block of steel, and you sandblast it. You shoot it with very high-speed sand particles. Those sand particles are going to transfer energy to metal atoms and make those metal atoms have enough kinetic energy to break free of their position. That's what happens when something melts. It's just that instead of using a sandblaster, you put in thermal energy in a different way. Now, when it melts, what I actually described would be sublimation, because that iron went essentially from solid phase to gas phase. When it melts, it breaks away from its position, but it still is held by surface tension, by the surface energy, the forces that are cohesive holding them together so that they can't escape completely. So melted, the molecules can move around freely, but they cannot escape. You give them more energy, they go fast enough, and they can pull away. So you should know that amount. Then we have pressure. Hydrostatic pressure, it's the same in all directions. You don't have more pressure horizontally than vertically. It's always the same in all directions. The force the pressure makes is always into a surface, and of course pressure is defined as the force on a surface divided by the area of that surface. So the force is always into the surface, which means the pressure can't be below zero because below zero would be out of the surface, and is related to force thusly. Then we need to be able to apply Pascal's principle, which says that the pressure here and the pressure here, if they're the same elevation and it's the same continuous fluid, will be the same. And Archimedes' principle that says that the buoyant force is equal to the weight of the fluid displaced, which gave us that equation, the density of the fluid times the volume displaced times G. Be able to use Archimedes' principle. We did a lab with that. Make sure you understand what we did in the lab. So that is our static fluids. Oh, yes, and surface tension. We did things like, how high can the water climb in a tube due to capillary action? So you should be able to do that. Yes, another problem. I put in problems here. Chapter 12 is fluid dynamics. Notice I crossed out Poiseuille's equation. Poiseuille's equation was at the very end of the last lecture. Remember, Wes had said something about my fire example not being very realistic. I said, yeah, next slide, we get to that. Poiseuille's equation is where we bring in the reality of pressure loss due to friction. So that if you force water to go through a hose, you're going to have pressure loss because there is friction between the walls of the hose and the water. You don't have to be able to use that. But you do have to be able to use the Bernoulli equation. So the fundamentals of the Bernoulli equation are using the work-energy relation, we were able to determine that pressure plus 1/2 density V squared plus density GH for a continuous fluid is a constant. It's like in your homework, you had to make the Bernoulli equation for here and the Bernoulli equation for here, but then since it's a constant, they're equal to each other and you can solve it. So what this tells us is if I have still fluid here and moving fluid here, the pressure difference between the two is going to be such that the moving fluid has a lower pressure. If I go to a different elevation, I have a pressure difference due to elevation. In fact, originally we had learned the equation change in pressure is rho g h. But that's incorporated into this equation, so we don't even need to think about it separately as long as we know the Bernoulli relation. And you do need to know the difference in laminar flow versus turbulent flow. Laminar flow is layers. Laminar flow occurs if something's going slow enough that the water is not torn apart and you don't have obstructions that are going to tear it apart. Turbulent flow, the water is being torn apart. It's not going in layers now. You have something that's causing it to make little bubbles, little vacuum gaps called cavitation. And so if something's going faster, then you have the speed difference between layers is larger and it can come apart, making turbulent flow, or obstructions can make turbulent flow, which is where the Reynolds numbers come in. Okay, now, wow, forgot. Let's work through as much of this as we can in 2 minutes. Jeremy's playing with a yo-yo of mass M equals 34 grams. The yo-yo string is let out to a length of R string is 42 centimeters, and he spins the yo-yo in a horizontal circle at a constant rate of 5.9 radians per second. The yo-yo string makes an angle of theta something with horizontal. So he's going like this. Okay, don't hit yourself. It's going like this in a circle. And it says use the PHYS diagram. We don't have it, but we can do it. What forces are acting on the yo-yo? There's what? Force of gravity, which by definition acts what direction? Down. I'm not going to, because we only have 1 minute left, I'm not going to sit and wait for somebody to give a wrong answer. That's it. If I was waiting for somebody to give a wrong answer, the wrong answer would have been, well, there's got to be a centripetal force because it's going in a circle. Why is that a wrong answer? It's not, it is the tension. It's the sum of the forces. So if I take these two forces, remember Newton's second law, sum of the force vectors is equal to MA. So if I add these, mg like this, force tension like that, then the resultant of those two must be equal to MA, which in this case is going to be the centripetal force. And so I can calculate based on the angle that they're giving me what that centripetal force is going to be already. So we got the correct free body diagram, calculate the tension of the string in newtons. Well, this is easy. With this triangle, how do I get this triangle? By applying Newton's second law. I can immediately say, well, this angle here is theta. That's theta, which means that this here is theta. So I'm going to have sine of theta is equal to mg over force of tension. And so it didn't take me very long at all to get force tension. Okay, we're out of time. I do have one more question to ask before I just let you go. Why was there no force normal on that? I forgot some people will say force normal. Yeah, it's not pushing on a surface. Force normal only occurs when you're pushing on a surface. Okay, have a great day. I'll see you for the test tomorrow. Be sure to respond to Ashley about coming to tutoring if you're going to be coming so she knows what to plan for. And, of course, remember my office is pretty much always open to you. For a second, I thought